Hello and welcome back to Calculus 1, section 3.8 on implicit differentiation. We are going to put that chain rule to work now. So, we know from pre-calculus that y equals f of x, notation for a function. We also know that we can denote derivative by dy dx. We can also denote derivative as f prime of x, and so on. We know that we can take second derivative, third derivative, fourth derivative, go as far and as high as we want or need for the application. It is time for us to discuss the notation and then move these derivatives out of the realm of just x and differentiate functions and other things. Well, differentiate functions in other way, and then also differentiate a non-function. So, why is dy dx really superior notation? What this means is you are taking the derivative in respect to x of your function y. Now we know that y is f of x, so this is the notation that is the best. This part over here is called the operator, and it's like instructions. Operator changes a function. We are going to learn integrals later. And actually there is a multiplication here. So we have the derivative of f of x, which is obviously a function. And then we've seen that we can have a composite function in here, in which case we have a chain rule. The question is there a way to differentiate something that it's not a function, a relation? And it turns out yes. So, how's that achieved? Well, before we get there, we have to understand that functions that you can express as y equals f of x, where you can isolate y, are called explicit functions. And the functions where you cannot do that so your function is f of x and then x, let's say equal to 0, cannot isolate y, are called implicit functions. Let me give you an example. Y equals sine x is explicit function. You see that y is on one side and x is on the other side. It's a single y, so we're all good. You know it's going to pass vertical line test and all of those things. But then we say y equals sine y, and I'd say minus x. This would be implicit function, because you cannot it's not implicit function, it's implicit relation. It's not a function. So you cannot solve for y. You cannot write y equals everything else. You have one y that is single and like linear, and one y that is buried within sine function. And there's nothing you can do to free this one up and combine it with the other. So we would like to know, is there a way to take the derivative of this? Because I don't care what this curve looks like. We can find out using the graphing tool what it looks like. You can also calculate the points and then connect them, like, you know, in the coloring book. Let me just go real quick and take a look at this graph. So y equals sine y minus x. Wow, interesting. All right, so graph is this. It's a squiggle like that. You can find tangent lines. You know that there are tangent lines, which means there is the derivative for something like this. So there has to be a way to find that derivative, and that would be what we call implicit differentiation. So now for implicit differentiation, we take derivatives term by term, also known as term-wise. So say that we have our function y equals sine y plus x minus x. And I want to take derivative of that function in respect to x. It is important to note that you are taking derivative in respect to x, because you can take derivative in respect to y as well. But let's do the x. So now, what is the derivative of y in respect to x? Well, y is a function of x, so it must be dy dx. Must be dy dx. Equals to the other side, and now you have the derivative of sine y. What is the derivative of sine y? Well, it has to be cosine y. But we have to multiply by the chain rule because it's a composite function. Sine y is a composite function. We know that y is equal to some f of x. We don't know what that f of x is, right? So y is some function f of x. So technically, if you write sine y, you are writing sine of f of x. Well, that's good for chain rule, right? Because in this case, right, you have f of x plugged into a sine. So function plugged in a function, that's our chain rule. So if I have that, that means that I have to follow with a chain, which is the derivative of the inner function. Inner function is y, therefore dy dx is the chain that follows. Minus 1, because you have derivative of x in respect to x is 1. Now, technically, you can also say I took the derivative of x in respect to x over there, but we'll deal with that later. So now, observe that I have two terms which contain dy dx. And all of the answers that we had so far in this class in terms of the derivative, they were all dy dx equals everything else over here. So now we need to factor dy dx, which means that we have to bring everything to the same side. So dy dx minus cosine y dy dx equals -1. Factor out dy dx, and you are left with 1 minus cosine y. And finally divide by that to get dy dx alone, because we are looking for the derivative. And if you want to make this prettier, you can write 1 minus cosine y minus 1, because swapping the order in subtraction, this is another algebra formula. If you have a minus b, that's equal to negative b minus a. If you interchange the order, right, here's a minus sign that pops out. So what I did is I interchanged the order on the bottom, the minus sign pops up, and then the negative and negative cancel, and we have the simplified version of the problem. I have the answer. Observe that your answer here is in terms of y. And that will happen often in these implicit, right? That you will have answer in terms of functions of y, which is okay. So if you take a look at the entire problem, we took derivative of each one of these terms separately. Derivative of y is just dy dx. Derivative of sine is cosine followed by the chain, because we were taking derivative of y. And then derivative of x is just 1. And then we follow the algebra. We make sure that we take all of the dy dx terms, put them on the same side, and factor it to get dy dx alone. All right, let's see. Find the derivative of e to the 3y minus x to the 6 is equal to 10xy. Again, you take graphing utility, right, the software, Mathematica, Desmos, whatever you like to use. You plug this in, and it will come up with some kind of curve. Now your job is to figure out what the derivative is for this monstrosity. Obviously, the software will find it for you anyway. So what you can do is you can go and differentiate this term by term. So what's the derivative of e to the 3y? It's going to be same like if there was an x up there. Yeah, 3e to the 3y. And then you have to follow by a chain dy dx. Because y is a function of x, and they are... y is a function of x, right? So now, minus 6x to the 5. If you want to follow it with a chain, you put dx over dx, but that cancels. So we don't have to worry about the chain for function that is x in respect to x. Equal to, and what do I have on the other side? I have a product rule, because I have a function x, which is linear function, multiplying function y. So we have the product rule here. Also known as the grade slayer on exams, because you don't do the product rule and obviously everything falls apart. So copy the first, 10x, derivative of y is 1, but we have to follow with the dy dx, plus copy the second times derivative of the first. Now the same rules. Everything with dy dx goes on the left, everything without dy dx goes on the right. So 3e to the 3y dy dx minus 10x dy dx is equal to 10y plus 6y over 5. So all of the terms with dy dx go left, and all of the terms without dy dx go to the right. Factor out dy dx to get 3e to the 3y minus 10x is equal to 10y plus, oh, this was supposed to be 6x to the 5, guys. 6x to the 5. There we go, fixed. And the answer is dy dx is, we have, right, we divide, so 10y plus 6x to the 5 divided by 3e to the 3y minus 10x. And that's it. So this is called implicit differentiation, when you are differentiating expressions that are not functions. Every time when you take the derivative of a variable that it's not the variable you had in the derivative, you have to follow with the chain rule. So now I just want to put in an example that has different letters for variables. Let's say you want to find the derivative in respect to m of e to the 2t plus 3y to the 8 minus 1 is equal to 14m minus 9g, whatever. All functions. All of these are functions. So what do? Well, you are taking derivative in respect to m. The only term that will not have a chain is the term that is m term, because the derivative and the variable match. Every single one of the other ones will have the chain rule with it. So 2e to the 2t, and then we have dt dm, plus the next term is y, so that's 24 y to the 7 dy dm. 1 goes to 0. The other side is 14 minus 9 dg dm, because we are differentiating g in respect to m. Now all of the terms with dg dm go on the left, so 14 is the only one that stays on the right. And if you are quick with this, you can actually, sorry, yeah, this is the end, because you can't factor, they're all different. You have dt, dy. Now, out of the problems that we did, this problem is one of the most important, because coming up, related rates, word problems, application problems, the one that you use to do your engineering and make money, is actually this. I'll give you an example. A cube of ice, we are going to have a lecture on this, obviously. Cube of ice with sides a, right, has a volume of a cubed. And that volume is going to shrink in time because ice melts. What's the formula? Well, I have to take the volume formula and differentiate that volume formula in time to get the rate at which the ice is melting. So when I take the derivative of v, I get 1, but we have to do the dv dt. Okay, I'll write 1 times dv dt is equal to 3a squared dA dt. So this is your implicit differentiation that you have to know to come up with a formula which relates the rate of loss of volume with the rate of loss of length of a side of a cube. And that should be common sense. As each edge of this one, of this cube, is getting shorter because ice is melting, the volume is getting smaller because you're losing ice. You're losing the volume of the object. So the skill of differentiating these formulas using implicit differentiation is extremely important because a lot of your work in engineering depends on understanding the changes in these quantities like volume and size and surface area, and we'll do all of this stuff when we get there. I think that's 3.11, so when we come back we'll have that. We'll talk about that stuff. So you need to really embrace this Leibniz notation because it makes stuff easier for us to understand. And we see the division. See, y prime or a v prime is a bad notation because you don't get to see the rate in there. But if you write dv dt, you immediately know it's a change in volume in time. So that's the way you read these formulas. Change of volume in time, change of amount of money in account in time, change of your height in time. Like all of these things, right? So these notations are bad because you can't really, right? These notations are bad because you can't really get the full picture of what's happening. Here's another reason why something like the Leibniz notation is great. See, if I write that my y function is equal to ax squared plus bx plus c, and I ask for the derivative. Now, standard thinking is that a, b, and c are constants, and right, coefficients and constants, and x squared and x are variable parts. So if you write y prime is equal to 2ax plus b, well, that's definitely the derivative of it, because the derivative of x squared is 2x, and you copy the constant in front, which is you copy a. Over here you copy b, the derivative of x is 1. That's okay. But then I bother you this way. I say y prime is also x squared, and y prime is also x, and y prime is also 1. And all of these formulas are valid. Can anyone tell me why? We know that we cannot have 4 different derivatives for the same function. We know that. But I am telling you right now that each one of these notations and derivatives are valid all at the same time. Now, how's that possible? Well, it's possible because if you are using this y prime notation, you can't understand and know. But if you use the correct notation, You know, this one is the function, derivative of the function in respect to x. The next one is the derivative of the function in respect to a. You see? Because who says that x must be the independent variable? You know, a can be independent variable as well. The next one is dy db, and finally dy dc. So these are different values. So you see that knowing it's important to know what variable you are taking the derivative in respect to and what are you taking the derivative of, which is the y part. So now I'm going to jump into homework, and we're going to do examples from homework. Oh, by the way, you get to plug in the chain rule and the product rule and the quotient rule in implicit differentiation now to make it more interesting. And you go from there. So the book really starts nicely. Y squared plus 3x equals 8 in problem 16. So you are supposed to differentiate that. Try it on your own. I'll give you 30 seconds. Right, so derivative of y squared is 2y, and we have to follow with a chain because the variable that we are taking the derivative of doesn't match the variable that we are taking the derivative in respect to. So we have to follow with a chain. Plus the derivative of 3x is 3. We can write dx over dx and then cancel it, so we don't have to. And finally, on the other side, we have derivative of 8 is 0. We move 3 to the other side and divide by 2y to get dy dx alone. So negative 3 over 2y. And that's it. That's the problem. What else is cool? Problem 20. It's getting spicy now. the derivative in respect to x of tangent xy is equal to x plus y. All right, try that one. All right, so I hope you see the product rule within tangent, which means you have product rule inside. You have the product rule inside the chain. And then you have x plus y on the other side. So the derivative of tangent is secant squared xy times the derivative of this product. Copy the first. Derivative of the second is 1 times dy dx, because we took derivative of y in respect to x. Plus copy y. Derivative of x is 1. and on the other side 1 plus dy dx. So now on the left hand side we have to FOIL or distribute, and then we can put all of the terms on the left and the right and be done. So the first one is x secant squared xy dy dx plus y secant squared xy is equal to 1 plus dy dx. Now all of the term with dy dx on the left, all the other ones without on the right. So x secant squared xy dy dx stays, minus dy dx is equal to 1 minus y secant squared xy. So this term goes this way, this term goes that way. To match them, now I can factor out dy dx and just have 1 minus y secant squared xy divided by x secant squared xy minus 1. And that's it. Observe that your derivative on the right side is in terms of x, and in terms of y clearly is going to be a mess because we are not having a function to begin with. We are using this on a relation. Problem 36. xy plus 1, everything cubed, is equal to x minus y squared plus 8. All right, let's take a look. So we have a product rule inside the chain again, and then all individual on the other side. That's easy. So 3 times xy plus 1 squared times the derivative of the inside, which is a product rule. So copy first, the derivative of the second is just dy dx, plus copy y, derivative of x is 1, equal to 1 minus 2y, again dy dx because we took derivative of y in respect to x, plus 0 for 8. So now we have to multiply by distribute on the left. So we have 3x xy plus 1 squared dy dx plus 3y xy plus 1 squared is equal to 1 minus 2y dy dx. Shuffle the terms. So the left side has dy dx, then the right side without. We have 3x xy plus 1 squared dy dx plus 2y dy dx y dx 3x xy plus 1 squared plus 2y is equal to 1 minus 3y xy plus 1. So we factor out dy dx and then divide by the stuff you want to get rid of. We're done. So 1 minus 3y xy plus 1 squared divided by 3x xy plus 1 squared plus 2y. And that's it. All right, don't all scream at once. One more and fine. Fine. Okay. One more. This is problem 40. The derivative of square root of x plus y squared is equal to sine y. All right, let's take a look at this together. So I'm going to rewrite the square root as a 1/2 exponent. And then go from there. So 1/2 x plus y to the negative 1/2 when I subtract this, times the derivative of the inside, which is 1 plus dy dx, because I am taking the derivative of x in respect to x, that's 1. Derivative of y is still 1, but I have to follow with the chain dy dx, equals to cosine y, and I have to have dy dx as well, because I took the derivative of y in respect to x. On the left hand side, I have to distribute. So the first term is 1 over 2 square root of x plus y, because the negative 1/2 is the square root in denominator because of the negative. 1/2, 2 is in denominator. So all I have in the numerator is this 1 times this 1, and 1 times 1 is 1. So that's all we need. And then we go plus. Now I have the same thing. 1 over 2 root x plus y, but it has dy dx attached to it, is equal to cosine y dy dx. So now you can move this term to the right side. So move this there, and we get 1 over 2 root x plus y is equal to, factor out dy dx, and you're left with a cosine y minus 1 over 2 root x plus y. So now dy dx is equal to 1 over 2 root x plus y divided by cosine y minus 1 over 2 root x plus y. And we don't like it to leave it here because you have a double fraction. So we use the algebra trick of multiplying by common denominator to kill off the double fraction. So multiply top and bottom by 2 root x plus y, 2 root x plus y, which gives us that dy dx is equal to, on top they cancel, so numerator only has 1. In denominator, we get 2 cosine y times the square root of x plus y minus 1, because they cancel. And that's it. I almost forgot. One more part to this. Higher order derivatives. This is a living nightmare, obviously, because when you take your first derivative, you end up with something like this. Then you have to take another derivative, which makes it living hell. So let's take a look. Find second derivative for problem 54. Says x to the 4 plus y to the 4 is equal to 64. Well, you start with the first derivative. And get 4x cubed plus 4y cubed is equal to 0. I forgot dy dx. Equal to 0. So 4y cubed dy dx is equal to negative 4x cubed. And when you divide, you get negative 4x cubed divided by 4y cubed. These cancel, and you get negative x cubed over y cubed. You can compress that into x over y everything cubed if you want to. Any one of these two answers is good answer. And now you need to differentiate that one more time. So you have the derivative equal to negative x cubed over y cubed, and you want to differentiate this again to get your second derivative. Well, d times d is d squared y over dx squared. That's the notation for the second derivative, and it's easily obtained. D times d is d squared, dx times dx is dx squared. It's very simple. Now, on the right hand side, you have the quotient rule. So you have your y to the 6, y cubed times the derivative of this is negative 3x squared, minus copy negative x cubed, times the derivative of y cubed is 3y squared dy dx. Can you leave your answer here? No, because you have dy dx. And you know what dy dx is. So plug in. So now we are clearing this up. I have negative 3x squared y cubed plus, now I have 3x cubed y squared, and dy dx is negative x cubed over y cubed, so there will be some canceling there, divided by y to the 6. So now we have these guys cancel. So the second derivative is negative 3x squared y cubed, again minus, and now you have 3x to the 6 divided by single y, and you have y to the 6 times y, because you want to get rid of that denominator, to give us negative 3x squared y to the 4th minus 3x to the 6 divided by y to the 7. I don't know if you're gaining anything by factoring out negative 3x squared, but we can factor. If you factor out negative 3x squared, you are left with y to the 4th minus plus, because we factor out negative, x to the 4th divided by y to the 7. I'll just put the word or, whatever, you know. Clearly, you will have to set this equal to 0, so the right-hand side. Actually, no, you're not setting these on to 0. Because we don't do graphing of implicit. So the cool thing here is to understand that at one point in life, which is this point in life here, right? We had the derivative, the first derivative, the part of our answer. And then we plugged in what that first derivative is, and then worked out more algebra to simplify as much as possible. So that is the implicit differentiation. We are using our chain rule in every problem. So when we come back, we are going to talk about the tangent lines. Now, this is not a lecture in a book. This is a part of every lecture in chapter 3. Is talking about the tangent line and problems with tangent lines. So I'm going to take all of those and push them into one lecture, because tangent line is the most important problem of chapter 3 and one of the most important problems of calculus in general, because it measures the change. So the next lecture does not have its lecture in a book, but it's the lecture that is spread across all sections of chapter 3. So we'll have everything in one shot. See you in 5.